One very important variant of Markov networks that is probably at this point more commonly used than other kinds, than anything that's not of this type, is what's called a conditional random field. So conditional random field, you can think of it as something that looks very much like a Markov network, but for a somewhat different purpose. So let's think about what we are trying to do here. This class of model is intended to deal with what we call task-specific prediction. That is, where we have a set of input variables or observed variables, x, and we have a set of target variables that we're trying to predict y. And this class of models is designed for those cases where we always have the same types of variables as the input variables and the same types of variables as the targets. And we're always trying to solve what is essentially the exact same problem, or the exact same type of problem. So let's think about that as, let's think about two examples along these lines. So again, going back to the example of image segmentation, here we have the input is always a set of pixels with their values, pixel values, which we can process to produce more expressive features like histograms of colors and textures, but this is sort of not relevant at this point, although it will be in a minute. So my input x is pixel values and processed features from those. And my target variables y is a class for every pixel. So for example, where by class I mean, grass, sky, cow, water, and so on. And we're always we design the model so as to solve this problem of going from x to y. And we want to solve that problem. In some of the text processing or NLP problems that we discussed, the input x are the words in a sentence. And the output that we're trying to derive is, for example, the labels of the words. Where again, the labels might be, in this case, things like person, location, organization, and so on. And once again, this is always our input, the words, and the output is always the labels. So what is the problem? So fine, so we want to solve this, this kind of prediction problem. Why not use just a regular old graphical model in the same way that we've done so far? So let's think about what some of the issues might be with that. So imagine that we are trying to predict, in this case, CI, which is the label of a particular superpixel, in this case, I. And we're going to go ahead and process our features of that superpixel to provide a range of different color and texture histograms that, that represent different ways of measuring the appearance of the superpixel. So in this case, that's my Y, just as a sort of in the notation of the previous slide, this is my target Y, and these guys down here are my X's. So what's the problem with this? The problem with this is that these features that are often much more informative about the class of the pixel are very correlated with each other. So, for example, the texture histograms, which tell us sort of the directions in which lines go in a particular superpixel, they're very redundant in terms of the kinds of structure, the kind of texture that they measure. And so if you have features here that are very correlated with each other, so where two features have a lot of redundant information, if we represent this in a naive Bayes model, as I drew here, where the features are independent, given the label, then I'm effectively ignoring that correlation structure. Now, why is that bad? It's bad because it allows me to count the same feature again and again and again and again and again. So if I have 5 copies of the feature, or 5 very correlated, related features that effectively measure the same thing, I count it 5 times, which means I get really confident because of this one feature. If I have 100 copies of that feature, I count it 100 times. So and again, it pushes me towards very skewed probability distributions that don't really, that are not really good reflections of my true beliefs, because they make incorrect independence assumptions. Well, fine. So let's make correct independence assumptions. Let's add a bunch of edges to capture the correlations. Well, that turns out to be really hard, because once you start doing things that are trivial features, figuring out how they're correlated is hard. And furthermore, even trying to put in these correlations gives rise to, so first of all, this is hard to figure out. And it gives rise to densely connected models. If I start putting in all these edges between these features. So a completely different solution to this problem basically says, well, I don't care about the image features. I don't want to predict the probability distributions over pixels. I don't care to predict, I'm not trying to do image synthesis. I don't care about the probability of having, a green pixel next to another green pixel next to a brown pixel. I'm trying to use a pre-given to me, something that is already given, which is the features X. And the only thing I really care about is to model the distribution over Y. So I've reformulated my problem. Instead of modeling the joint distribution of X and Y together, so instead of doing this, I'm going to model a conditional distribution of Y given X, where I'm not trying to capture the distribution over X. Now, if I'm not trying to capture the distribution over X, then I don't really care about the correlations between them. And we'll see that a little bit more clearly when we look at an example in a bit. But before we do that, let's first give ourselves the formal definition of this thing, which is called a CRF, which stands for conditional random field. And a conditional random field at first glance looks just like a Gibbs distribution. So just like a Gibbs distribution, we have a set of factors, each with their scope. And just like a Gibbs distribution, I multiply the factors to get an unnormalized measure. And now, so far it's exactly the same, except that I have an X and a Y as the arguments of the unnormalized measure rather than just a set of random variables. This is where the difference comes in. If I want to model a conditional distribution of Y given X, I'm going to have to put X on the right-hand side of the conditioning bar, which means I'm going to have a separate normalization constant, or partition function, that is a function of X. And so what does that mean? It means that for any given X, I sum over Y, which means that for any given X, I'm going to have the sum of all of the Y's that correspond to that X. And then I'm going to construct a conditional distribution by normalizing I'm going to construct a conditional distribution for Y over Y for any given X. This shouldn't have a tilde, by dividing by this X-specific partition function. So to be a little bit more concrete, let's imagine that I have a table here, and I'm going to make life simple for myself, and this is my table for x1y, x0, y0, x0, y1, x1, y0, and x1, y1. And for any given x, in this case, for example, these two entries right here, I'm going to sum them up. That's going to give me the normalizing constant for these two entries together, and then I'm going to divide by that z of x0, and that guarantees that these two entries now sum to 1 because I just basically divided by their appropriate normalizing constant. And similarly, I'm going to add these over here, and I'm going to divide this entry by z of x1. And so I've now defined a family of conditional distributions. So this is a family of conditional distributions. Which varies by x. Now, it turns out that CRFs are highly related to a model that we have previously seen in many machine learning classes, and also comes up as a CPD representation in Bayesian network, which is the logistic function or the logistic model. So in order to understand that connection, let's look at a very, very simple case where we have both x's and y's are binary random variables. So they take on values in the space 0, 1. And we're going to use in our log linear model a simple representation of my log linear features, which is just the indicator function. So we have 1, my indicator function is 1 when both xi and y, when xi and y are both 1, and 0 otherwise. And that's going to have a parameter yi. And now let's actually plug that into the CRF representation and see what happens. So let's look at phi I of xi and y equals 1. Well, if you look at that, in this case, y is always 1. And now we have two choices. Either xi is 1, in which case the indicator function is 1, or xi is 0, in which case the indicator function is 0. So you can rewrite this as wi times xi. Exp of wi xi. Right? Because if xi is 0, then you get exp of wi times 0, and if xi is 1, you get exp of wi. On the other hand, if I make y equals 0, then my indicator function is 0, because if y is 0, then the indicator function is 0, and at that point I get exponential of 0, which is equal to 1. Okay, so these are my two cases. I have what is the value of this factor for y equals 1, and what is the value of this factor for y equals 0, and now I can go ahead and compute my unnormalized density. And my unnormalized density has the following, again, I'm going to do two separate cases. There is the case when y equals 0 and the case when y equals 1. And my unnormalized density in the case y equals 1 is just multiplying all of these guys up here. So multiplying all these guys, which gives rise to this exponential over here, just because the product of a bunch of exponentials is the exponential of the sum. Okay, so that is in this case, and here clearly the product of a bunch of 1s is 1. So that's pretty straightforward. And so now putting this all together to produce a normalized density, remember, my goal is to produce a density, a normalized density, which is the P of y, my binary value y, given all of the features x. And if you just stick this together, this is, when you just rewrite this, this is the probability of y equals 1 comma x, and this is divided by the probability of y equals 1 comma x plus the probability of y equals 0 comma x, which is my normalizing constant. Well, This is a very familiar shape. It's the sigmoid function. It's e to the power of z, if we call this z. So it's e to the z divided by 1 plus e to the z, which is exactly my sigmoid function. So what we have concluded from this is that the logistic model is a very simple CRF. So broadening from this particular mathematical derivation, what we have here is that if we were to think about the model where we had a joint density of y and x together as a kind of a naive Bayes model, because we only have pairwise terms that relate the y and the xi. So you can think of it as a bunch. If we weren't doing this conditional normalization, we would have a model that looks like this. We would have, the y, and we would have a pairwise feature that relates y to x1, y to x2, up to y to xn. And that would be effectively like a naive Bayes model, because since we don't have any features, pairwise features that connect the xi's to each other, we would effectively have a model where the xi's are independent given the y. So if I weren't doing a conditional model, if I were to just use this set of potentials to represent the joint distribution of x and y, it would be effectively like a naive Bayes model. And it would make very strong independence assumptions. But because I'm modeling this as a conditional distribution, like this is the conditional distribution, I've effectively removed from this analysis any notion of the correlations between the x's, and I'm just modeling how the x's come together to affect the probability of y. And so that's really the difference between a naive Bayes model and a logistic regression model. And that same intuition extends to much richer classes of models where I don't just have binary variables in a single y, but rather a very rich set of y's and x's. And nevertheless, this ability to sort of ignore the distribution over the features and focus only on the target variables allows me to allows me to sort of ignore correlations between rich features and not worry about whether they're independent of each other or not. So for example, going back to our notion of CRFs for image segmentation, here we typically have very rich features of the variables. So for example, when we think about individual node potentials that relate the features xi to the class label yi, we don't worry about how correlated the features are. We can have color histograms, texture features. You can have discriminative patches like looking for the eye of the cow, for example. And all of these are going to be really correlated with each other, but I don't care. You can even look at features that are outside of the superpixel. You can say, oh, well, if it's green underneath in a completely different superpixel, maybe it's more likely to be a cow or a sheep because they tend to be on grass. That's cool too. These are definitely correlated because you're counting the same feature for my superpixel as well as for a different superpixel. That's fine. I don't care because I'm not worried about the correlations between the superpixels. So the correlations don't matter. You can even, and this is very commonly done, train your favorite discriminative classifier, a support vector machine, boosting, random forest, anything that you like, to predict the probability of yi given a whole bunch of image features x, and that's fine too. And in fact, that is how one achieves high performance on most of these tasks, by training very strong classifiers for, in most cases, your node potentials, that is the predictors for individual variables, and then adding on top of that pairwise features, or not just pairwise, but a higher order features between the y's. It's important. One important point here that is useful to make is that the word features is overloaded in this framework. And that might be confusing, and rightfully so. There are features in the context of image features, for example, like these guys over here, and that's one use of the word features. And the other use of the word features, which is this usage, is in terms of features in my log linear model. And these Fs that we use to define the log linear model. And features are actually used for both, which is an unfortunate thing, but there it is. So hopefully this will be clear from context. The same kind of idea applies when we do CRFs for language. Again, we usually have here features that are very highly correlated with each other. So, for example, whether the word is capitalized is correlated with whether the word is in some atlas or name list. Definitely correlated features, correlated with whether the previous word is Mrs. or Mr. All sorts of other features that are often very correlated with each other. You can even see that this word is used as a feature for more than one word. That's fine. It's not a problem because we don't try and model this distribution over the words in the sentence, but rather the probability of the labels given the words. So to summarize, a CRF is deceptively like any other Gibbs distribution, but a subtle but critical difference is that it's normalized differently. It's normalized so that you're creating a conditional distribution on y given x. And we've seen that as a special case, it subsumes your standard logistic regression model, but has a lot of other, but has a much richer expressive power. A key feature of it is that we don't need to model the distribution over variables that we don't care about, only the ones that we actually care about predicting. And that a critical utility of this is that you can design really, really expressive predictors of pieces of the model without worrying about incorrect independencies between different variables, which would be inevitable if you actually tried to model this distribution, joint distribution over these expressive features.